Space exploration is a war against scale. We humans evolved on planes where far away meant a walk of a few days, but the universe does not operate on our scale. The universe operates at distances that humble our imagination and challenge our engineering. To fight those distances, we built monsters and the king of all monsters. The definitive silhouette of our audacity was the Saturn V, a tower 110 meters tall, fueled by the dream of an entire species and the violent chemistry of kerosene and liquid oxygen. We know what it did. It roared into the skies of Florida, broke the chains of gravity, and delivered men to the moon. But the moon, in cosmic terms, is our backyard. Today, we're going to run a thought experiment of epic proportions. We're going to take the Saturn V at the peak of its performance. Maximum speed, 40,320 kilometers per hour. And we are not going to slow down. We'll turn the Saturn V into an interstellar cruise ship, pedal to the floor. Destination: every planet in our solar system. How long would it take to reach Mercury, Mars, or the giants like Jupiter and Saturn? What about the dark, distant worlds like Neptune and Pluto? The answer will completely change how you perceive the scale of the solar system and humble our understanding of what far truly means. To understand how far the planets are, we need to understand how the Saturn V actually behaved on its original mission, the moon. When the 5 F1 engines of the first stage ignited, the goal was not speed, it was force. Lifting 3,000 tons off the ground, the work of 60,000 humans, concentrated in 5 metal cylinders. Real speed only came much later, after the first 2 stages were discarded, after the spacecraft was orbiting Earth. That's when the magic happened. The third stage, the SIVB, ignited in the vacuum. This was the TLI maneuver, translunar injection. For 6 minutes, the J2 engine pushed the crew back into their seats, accelerating from 28,000 kilometers per hour to 40,320. That is our magic number, 40,320 kilometers H. Escape velocity. Today, we never slow down. Pedal to the floor. And now, with the Saturn V hurtling at maximum speed, let's explore how long this monster would take to reach each planet in the solar system. Starting with the simplest baseline, the destination it was born to conquer. In real life, Apollo missions took 3 days to reach the moon, about 72 to 75 hours. But wait, the moon is 384,400 kilometers away. Divide by 40,000. The trip should take only 9.5 hours. Why did it take 3 days? Because in real space, gravity is a brake. The moment the Saturn V engine shut down, Earth began pulling the spacecraft back, like rolling a ball uphill. The spacecraft spent the entire journey losing speed, climbing a gravitational hill. By the time they reached the moon, they were no longer traveling at 40,000 kilometers knot, but at about 3,000. But today, in our hypothetical scenario, we're going to ignore that brake. We keep the pedal to the floor. Speed locked at 40,320 kilometers H at constant 40,320 kilometers H. We would reach the moon in less than 10 hours. You could leave Earth at breakfast and land in the Sea of Tranquility in time for dinner. Sounds fast, right? 40,000 kilometers. H is Mach 32. 32 times the speed of sound. Fast enough to circle the entire Earth in 1 hour. faster than any aircraft ever flown, faster than any rocket except those designed to escape planets. But now, let's see how that impressive speed behaves when the target is not the moon. When we turn our gaze farther, when we point the Saturn V not toward our satellite, but toward the other planets in the solar system. This is where things become humbling, because the moon, as I said, is just our backyard. It's only 384,000 kilometers away. In cosmic terms, that's not even a sneeze. The planets, that's an entirely different story. First stop, Mercury. We turn the rocket toward the Sunday average distance, 91 million kilometers, at 40,320 kilometers each, 2,257 hours. That's 94 days, 3 months. You are inside your capsule. The sun grows larger in the window with each passing day, more hostile. The spacecraft's cooling system working at its limit. Outside, temperature rising, radiation increasing. 94 days, just to reach the first planet. 3 months floating in vacuum, watching our star grow from a familiar light source into an increasingly close threatening fireball. Now, Venus, our closest neighbor, at its closest approach, just 40 million kilometers away, 41 days, just over a month, an old sea voyage between Europe and the Americas. In 41 days, you would see clouds of sulfuric acid filling your window, the hottest planet in the solar system. So far, it seems doable. 40 days, 90 days. You could imagine surviving that. But now, Mars, the dream, the destination von Braun had in mind when he designed the Saturn V distance to Mars, varies dramatically. Best case, 54 million km. Worst case, 401 million km. We'll use the average mission distance, 225 million kilometers. 225 million divided by 40,325,580 hours. That's 232 days, almost 8 months. You would miss 2 birthdays, 2 Christmases, watch governments change on Earth. Seasons come and go. You would age in the darkness. The moon took 3 days. Mars takes 230 days. A jump in magnitude of nearly 100 times. Let that sink in, from 3 days to nearly a year. With the same rocket, same speed. The only difference? Distance. And you still wouldn't have reached the giants. Take a deep breath. The easy part is over. Because what we just learned about Mars is a lesson in patience. But what's coming is a lesson in isolation, in darkness, in what distance truly means when you move beyond the small rocky planets and enter the realm of the gas giants. We cross the asteroid belt, which is actually very empty. Despite appearances in movies, the reality is you could fly through the asteroid belt and never see a single rock. The distances between asteroids are measured in millions of kilometers. It's a desert, a vast emptiness. The sun is now just a very bright star. No longer the disk of fire we know. Its light weaker, its heat more distant. You're in a place where sunlight takes over 40 minutes to arrive. If the sun exploded right now, you wouldn't know for nearly an hour. Jupiter, the gas giant that protects and threatens Earth. Average distance, 750 million kilometers. 750 million divided by 40,320. $18,600 in 10 hours. 2 years and 1 month. Let that weight sink in. 2 years of travel. Imagine boarding the Saturn V today. You would only arrive at Jupiter in 2027. You would miss 2 birthdays, 2 Christmases. Watch governments change, all while floating in the void. 2 years staring at the same black sky, 2 years breathing the same recycled air, 2 years eating the same packaged food, 2 years hearing the same hum of life support systems, 2 years without wind, without rain, without the smell of fresh cut grass or morning coffee, just metal, plastic, and endless void. And upon arrival, lethal radiation. Jupiter's magnetic field would fry Apollo's electronics in hours. The radiation belts around Jupiter are so intense, astronauts would receive fatal doses after just days in orbit. But visually, what a sight. A ball of gas that could swallow 1,300 Earths. The Great Red Spot, a storm larger than our entire planet. Cloud bands swirling at speeds of hundreds of kilometers per hour. But we cannot stop. Jupiter is only the gatekeeper of the outer solar system. The rocket is called Saturn V. Nothing more fitting than taking it to its father, Saturn, the Lord of the Rings. The distance doubles. Average 1.3 billion kilometers. 32,242 hours. Almost 4 years. A child born on the day of your launch would already be starting preschool when you first saw the glorious rings of Saturn. 4 years. A newborn would learn to speak, learn to walk, begin reading, all while you're floating in darkness, watching unchanging stars through the window at 40,000 kilometers per hour. It would take 4 years just to deliver a pizza to Saturn. Here, sunlight is weak. Conventional solar panels no longer work. You would need nuclear power to keep warm. Outside temperature, negative 140 degrees Celsius. Absolute cold. Saturn is the limit of what we can easily see from Earth with the naked eye. Beyond it, we enter the realm of darkness. Notice the pattern. Moon, 10 hours. Mercury, 94 days. Mars, 232 days. Jupiter, 2 years. Saturn, 4 years. The solar system is not linear. It is exponential. And we're only halfway. Uranus, a mystery visited only once, briefly, by Voyager, in 1986. It is a world of ice, water, and methane, spinning on its side. Distance, 2.9 billion kilometers, 71,924 hours, 8 years and 2 months. Isolation here would be utterly absolute. Radio signals traveling at the speed of light would take 2.5 hours to reach Earth, and another 2.5 to return. If you say hello, the reply only arrives 5 hours later. By then, the moment has passed. Conversation. Impossible. You're talking to ghosts. Voices from 5 hours ago. 8 years. Imagine that. You board in 2025. You wouldn't reach Uranus until 2033. A newborn child when you depart would be in 3rd grade when you arrive. Wars could start and end. Presidents would be elected and serve full terms. Technology on Earth would evolve. Everyone you know would age. And you? You would age in darkness, staring at the same sky, breathing the same air, hearing the same hum. 8 years without real sunlight, without blue skies, without clouds, without seasons, just cold metal and endless void. And upon arrival, a pale blue disk, no striking features, lost in eternal twilight. Uranus doesn't even give you a visual reward for your journey. It's just there, silent, cold, indifferent. But we're not done yet. Neptune, the last official planet, the god of the deep seas. Distance, 4.5 billion kilometers, 111,607 hours, 12 years and 9 months, almost 13 years. 13 years locked inside a capsule. For comparison, Voyager 2 took 12 years to reach Neptune. Wait, how did Voyager get there in the same time as our hypothetical constant maximum speed Saturn V? Gravity assist. Voyager didn't travel in a straight line. It stole energy from Jupiter and Saturn. By passing Jupiter, Voyager accelerated far beyond 40,000 kilometers h at certain moments, 60,000, 70,000 kilometers. Our best brute force engineering, the Saturn V, loses to the intelligence of using planetary gravity as a slingshot. This is why we need to be smarter, not just stronger. This is why space science is about mathematics and physics, not just bigger engines. But we're not finished. There's one more stop. Yes, it was demoted to a dwarf planet. But in this journey, it is the finish line of the classical solar system, Pluto. Average distance, 5.9 billion kilometers, 146,329 hours, 16 years and 8 months, 16 and a half years. A child born at liftoff would be getting a driver's license. When you pass the frozen world of Pluto, at Pluto, the sun is no longer a disk. It is just a star. The brightest in the sky, yes, but incapable of providing heat. Temperature, negative 240 degrees Celsius. If you turned off the heaters, you would freeze in minutes. The oxygen in the tanks would turn liquid and then solid. 16 years to cross our solar system at 40,000 kilometers per hour. A speed we thought was fast. A speed fast enough to get us to the moon in 10 hours. But for the solar system, it's almost static. Almost standing still. That puts into perspective what interstellar travel really means. The nearest star, Proxima Centauri, 40 trillion kilometers. If we maintained this Saturn V speed, it would not take 16 years. It would take 113,000 years. Modern human civilization is only about 6,000 years old. We would have to live, die, and evolve inside the spacecraft for millennia. That's not a journey. That's a migration of an entire species. So, what does this experiment teach us? It teaches us to respect the void. The Saturn V was the pinnacle of chemical engineering. It turned fire into motion in a way we had never seen before. It was perfect for the moon. The moon is right next door, 3 days away. But for the solar system, chemical rockets like the Saturn V are canoes trying to cross the Pacific Ocean. 40,000 kilometers, H is incredibly fast. For a primate evolved on the African savannas, but for the universe, it is almost static. To conquer the solar system, to truly colonize Mars, mine asteroids, float in the clouds of Venus, we need more than fire. We need nuclear propulsion, ion engines, solar sails, or technologies we haven't even dreamed of yet. The Saturn V opened the door for us. It showed us that we can leave home. But the road is far too long to travel with a 1969 gas tank. This is the truth we must face. Distances in space are not measured in kilometers. They are measured in years, in decades, in lifetimes. Space doesn't care about our ambitions. It doesn't care about our engineering. It's just there. Vast, cold, indifferent, waiting for us to become smart enough to cross it, not through brute force, but through cleverness, through science, through patience. The solar system is vast, cold, and indifferent. But every kilometer of those billions we calculated today is waiting to be traveled. Maybe not at 40,000 kilometers H, but much, much faster. While we talk, the Voyager probes are still out there, far beyond Pluto, carrying the golden record, silently navigating the infinite, proving that, slow or fast, we will always explore. From this distance, Earth is just a pale blue dot, suspended in a sunbeam, and someday we will leave that dot, not in canoes, but in ships worthy of the void. We will build new engines. We will harness gravity. We will bend space, or we will discover ways that even our imagination today cannot grasp.